spaces may be completely different. One of them may be projective, another not. So, and in fact, we kind of exactly this problem and related problem we discussed with Bernick in the article about some kind of about rationality, and it's amazing how many different cases occur already here. So if you have many points, then you obtain just a zoo of, let's say, projective and non-projective three-dimensional. So and something similar happens in the case of Kessler. So nothing. So therefore, here what I want to say is that this model is not exactly modeled. So it's not. There are points where you have many models, but finite number. Okay. So. Okay, now what I wanted actually to say that, so the picture is very similar for this Q, so for over some devices, dense set of devices, so you have a quadric, you have a condition kind of V, Q of V, let's say greater than 0, so Riemann type condition. So it's an open piece of the quadric which parameterizes you what's a Hodge data of such varieties, of your deformation. Now the problem is, now we would like to say, okay, where are Lagrangian fibration? Again, we certainly have devices. And these are devices, kind of Q of D equal Q of X equal to 0. These are potentially devices.
Sorry, but this form Q isn't it on H2, so how do we evaluate on W?
It's on H2. So form is on H2.
But you evaluated on W, wedge W bar.
Yeah.
W is what now?
No. Look, they have Q is a form on H2. Q is a form H2 XC to C in some H4. But it's a map to C. That's important. Where this class is placed here is another story. It's basically something like proportional to C2. Okay, so now we have this form. This form on some integer classes is greater than 0. There is a con, yes, and so Q of X is greater than 0 is a standard. So we have a standard picture. These are potential ample.
What's the signature of this form?
Sorry?
What's the signature of this form?
The signature is 3 something usually.
Like A3?
Yeah, like I said, it's all kind of, surprisingly enough, it all imitates K3. So many things are like in K3, but here they kind of sense is different. So there are this form, and then there is a boundary of this column. And so if this element is algebraic, Q of X, Q of D, so suppose you have Q of X is equal to 0. So this Q of X is equal to 0. So in case of K3, if you have an integer solution in the Picard group Q of X equal to 0, we guarantee the existence. There is a slide, so it's not maybe in this class, but there is a Lagrangian fibration. And we would like to say the same in general. So in principle,
also. So
sorry?
we need to assume left for K3
Sorry?
numerically effective.
Yeah, you need effective, you need something more. You can build a Lagrangian fibration maybe with another class. Yeah? So here, you have, so what I mean by D have been given the Lagrangian fibration.
I'm sorry, Fedor. So Grish's question was about this inequality Q of W of H W bar. So what does it mean? So, and the inequality you wrote.
No, Q of V. No, okay. In fact, this is kind of Q of V equal to 0. So Q of P equal to 0 is something which tells you how to say. So Q of P equal to 0 on the one hand tells you that this element can potentially be realized by holomorphic form, 2-0 holomorphic form. On the other hand, basically after rotation, when you go to H11, and this is an integer element, then this is potentially potentially a divisor corresponding to Lagrangian fibration. So what means corresponding to Lagrangian fibration? That means you have a map to B. There is a positive ample divisor here, D here, and D here, and then the preimage of this divisor. Fibration is a divisor, so D prime, and then G and D prime. D prime is a divisor, divisor D with Q of D equal to 0. And indeed, you see this divisor at most, how to say, the intersection of this divisor here is at most up to the dimension of this space. So D, the property is D to the power is equal to 0. Power n plus 1. So it's a similar topological condition, but on one condition tells you about the existence of holomorphic form with this class. Another condition tells you, if you interpret it, if you can move this class to H11, and it happens to be integer, it tells you potentially that it would give you a Lagrangian fibration.
I'm sorry, I'm missing something. You started with O minus 1 plus O minus 1 bundle over P1,
yeah,
which is a Calabi-Yau. Where is the first step? Right, it's a Calabi-Yau. With this first step, you start making a fibration. Where should I look?
No, that's different.
Oh.
So that was an example of non-trivial holomorphic transformation between smooth varieties, which kind of keeps your trivial canonical class. Yeah. No, that's a different. That was not an example for hyperkahler. It is not in hyperkahler we have a similar but much more complicated construction with P2 and cotangent bundle as a marker. So we have a similar construction of what is the trivial flow, simple flow, which gives you 2-0.
But where's the fibration? Where do you start writing this fibration over here?
No, this fibration is Lagrangian. That's what I did yesterday.
But you start with a variety. You need to start constructing this fibration.
Yeah. So how do we do on case resurface? On case resurface, if you have D squared equal to D, if you have D in pk of x, with D squared equal to 0, then there is this x, then there exists D prime, which is simply a fiber of Lagrangian fibration. So that's an old theorem, I don't know, Shparevich or maybe some. So there is a simple, purely kind of topological criterion on H11. You have a class, you get a Lagrangian fibration. And now we would like to get the same for all manifolds. And potentially, it's easy to give, potentially. Potentially, if we have a divisor, so we have all these subsets here, that's, this subspace is a codimension 1 again subspace. So moduli space is, let's say, okay, this is Q. M is equal to B2 of x minus 1, yeah. And we have a quadric in this subspace, and then there is a condition for a class to be algebraic, which is given by a divisor. And then if you enter, so we presume this is class D. D is the divisor. So for every element, Q of D equals 0. This is just for one form. We have a codimensional divisor in let's say, in this BQ, in Q, such that D for such structures